So here we go on Lesson C of Unit 2, Forces and Newton's Laws. Today we're talking about Newton's third law, and our learning target is to be able to understand that every force is part of an interaction between two objects and be able to identify these action-reaction pairs. So here we go. So far we've considered forces that act only on a single object, but a more complete analysis of forces shows that all forces are part of an interaction between one thing and another. Think about pushing on a wall. You are interacting with the wall, which pushes back on you with the same amount of force with which you push on it. A simple test of this is to push your fingers together and notice the discoloration on them. As you push harder, the discoloration is the same for both. They both experience the same amount of force. Or you can stand on a bathroom scale. Your weight, which is due to the earth pulling down on you, pushes down on the scale. So your weight pushes down on the scale. The scale pushes back on you with a force equal to your weight. All forces come in pairs that we call action-reaction pairs. And this is summed up in Newton's third law. Newton's third law says that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. We can call one force, say, the action force, and another of these forces the reaction force. Now, it doesn't matter which force we call action and which we call reaction. The important thing is that they are co-parts of a single interaction and that neither force exists without the other. Examples of action and reaction forces are all around us. Every time you walk, you experience them. When you walk, you interact with the floor. You push against the floor, and the floor pushes against you. The pair of forces occurs at the same time, but on two different objects. And that's really the key to understanding Newton's third law. It's that understanding that while all forces come in action-reaction pairs, the action force and reaction force act on two different objects. So when you drive down the road, the tires of your car push against the road while the road pushes back on the tires. In swimming, you push against the water while the water simultaneously pushes you forward. Rockets work because the rocket pushes the gas, pushes on the gas in the rocket, and the gas pushes up back on the rocket. When a hammer hits a nail, the nail exerts an equal force back on the hammer. These action and reaction forces happen even with what are called field forces. That's forces that do not require contact between two objects. Weight is a field force caused by Earth's gravitational field. So when you drop a ball, Earth's gravitational field pulls it downward. That's the action force. The reaction force, then, is the ball's gravitational field pulling up on the Earth. An interesting question often arises at this point in learning about Newton's third law. That question is, since action and reaction forces are equal and opposite, why don't they cancel to zero? The answer to this question is because the action and reaction forces act on two different objects. So here's how this works. Imagine we have an orange in a wagon. There's a force acting on the orange in wagon that pulls the wagon forward, and when this force acts on the system of orange and wagon, the system accelerates. When we look at this system, we don't worry about where this force comes from. We just know that a force acts and we get acceleration. Now when we add in the apple, we see that the source of the force on the wagon is this apple. Newton's third law tells us that the orange and wagon pull back on the apple just as hard as the apple pulls on them. The force on the orange provided by the apple is not canceled by the reaction force on the apple. The orange still accelerates because we're considering just the orange and wagon here as our system. Now let's consider a larger system. Let's go ahead and expand our system to include both the orange and the apple. We see here that the system, which we bound by this dotted line, makes the force pair internal to the orange apple system. So in this case, the forces do cancel because we're considering our system to be both the orange and the apple. A force external to this system is needed to accelerate it. So where does that force come from? In this final picture, we see that the force comes from the friction from the floor here. When the apple pushes against the floor simultaneously pushes on the apple, providing an external force, so there is an acceleration to the right. So action-reaction pairs don't cancel to zero because they act on two different objects. In each of these cases, when we get an acceleration, it's because that there is some external object providing that force to give that acceleration. When we consider both the orange and apple, that external force is coming from the floor to the apple to provide that acceleration. When we consider just the orange as our system, that external force is coming from the apple onto the orange. So imagine you're happily driving along and a bug hits your windshield. Which object experiences the greater force? Well, Newton's third law tells us that the force experienced by your car is equal to the force experienced by the bug. The two forces are equal and opposite. So why is it that the bug has such a life-altering experience? To answer this, we have to consider the masses of the two objects. So let's imagine that the car has a mass of, say, 1,500 kilograms, while the bug has a mass of just, say, 0.01 kilograms. Now, Newton's second law tells us that the net force for each of these objects is equal to its mass times acceleration. So this is the mass of the car times its acceleration. This is the mass of the bug times its acceleration. Now, Newton's third law tells us then that this force that's experienced by both the car and the bug are equal. So if we imagine that this force is, say, let's just say that it's 10 newtons. So it's 10 Newton force experienced by the car at 1,500 kilograms. It ends up having an acceleration of 0.007 meters per second squared. While the bug, Newton's third law tells us that the bug experiences a 10 Newton force as well, but with its mass of 0.01 kilograms, its acceleration ends up being 1,000 meters per second squared. That's a huge difference in acceleration, and it's because the masses of the two objects are so different that we get these massively different accelerations. So the bug here experiences such a greater life-changing experience than the car because it's so much smaller in mass, it experiences this much, much greater acceleration. So just as we said earlier, when you walk, you push on the earth pushes back on you. The reason we can't tell that the earth is accelerated, though, is because of the huge difference in mass between you and the earth. The same principle works with rockets. Rockets expel gas out of them. That gas, the rocket pushes on that gas. The gas pushes back on the rocket, and that's how we get rockets to launch into space. So to wrap things up, we can summarize Newton's three laws. Newton's first law, the law of inertia. An object at rest tends to remain at rest. An object in motion tends to remain in motion at constant speed along a straight line path. This property of objects to resist change in motion is called inertia. Mass is a measure of inertia. Objects will undergo changes in motion only in the presence of a net force. Newton's second law is the law of acceleration. When a net force acts on an object, the object will accelerate. The acceleration is directly proportional to the net force and inversely proportional to the mass. Symbolically, then, we write that acceleration is equal to the force over the mass, or more commonly, F equals ma. When objects fall, so acceleration is always in the direction of that net force. When objects fall in a vacuum, the net force is simply the weight, and the acceleration is g, and that g is the acceleration due to gravity. When objects fall in air, the net force is equal to the weight minus the force of air resistance, and the acceleration is less than g. If and when the force of air resistance equals the weight of a falling object, acceleration ends and the object falls at a constant speed, which we call the terminal speed. Then there's Newton's third law, the law of action-reaction. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Forces occur in pairs, one action and the other reaction, which together constitute the interaction between one object and the other. Action and reaction always occur simultaneously and act on different objects. Neither force exists without the other. So Isaac Newton's three laws of motion are rules of nature that enable us to see how so many things connect with one another. And we see these rules at play in our everyday environment. From here, you're going to want to make sure that you are reviewing your reading packet and be ready to complete practice exercises in class. See you then.